let's get back to JEE Live. And everybody, this is our session number 7. Your class teachers are saying hello to all of you. This is our second last session on fluid mechanics. Okay, I hope everybody is having a good time so far with fluid mechanics. So far in fluids, we have spoken about fluid statics. First, we spoke about the ideal fluids. Remember, I told you guys that first discussion will be about ideal fluids. In ideal fluids, we'll speak about fluids which are static, fluids which are dynamic. That means fluids which are inside a container and container inside they are inside container and are stationary. Container is also stationary. The second case is when they are inside a pipe and they are flowing. So we just completed our discussion about the fluid mechanics, fluid motion, and that to ideal fluid. So we have completed our discussion about ideal fluid. So today our discussion will move towards real fluids. We'll be speaking about something which is going to be practically present in the fluids that we deal with. Okay, just a second. Okay, everybody's ready. Shall we start? Everyone is ready? Good, awesome. Okay, everybody, so switching off the chat so that we focus on the screen. First, we'll obviously do a recap of what we did last time. There were very limited things that we learned last time. We spoke about the applications of Bernoulli's equation or Bernoulli's theorem. One very important thing we understood was velocity of efflux, in which we realized that when we have a container in which liquid is filled, and if you create a hole at some depth h, then the velocity with which your liquid is going to come out is under root 2gh. Remember, this h is the height above the hole to which the liquid is filled, and h minus h is, you can say, the distance of the ground from the hole, the vertical distance. So if you want to find out how far horizontally your liquid is going to fall, it's going to be 2 times h minus h into small h. That's the range to which your liquid is going to fall and hit the ground. Right? That's basically velocity of efflux. It was discussed by Torricelli, I think. Yeah, Evangelista Torricelli. He came up with this discussion. Then we spoke about another Italian person coming up with Venturi meter, which helps us talk about the velocity with which a liquid is flowing in a given tube. So we connect a tube which has relatively smaller cross-section area. Maybe the area of that smaller tube is small a, and capital A is the area of the main tube. And we are interested in finding the velocity of the liquid in the main tube. Okay, so we kind of have this arrangement where we can say that the tube is going to have area of cross-section capital A. Then we will have a smaller tube whose area of cross-section is going to be small a. Okay, so maybe something of this sort I can draw. Okay, so what we did, we realized that okay, if we connect this, and then to take care of the pressure difference, we connect this also with a U tube. Yes, not that U tube, but the tube which will connect to a manometer eventually, right, everyone? So from here, we connected it with a manometer. That manometer had mercury in it. So difference of this height is something that you can measure. And here the pressure is P2, here is the pressure P1. This is where I'm interested in finding the velocity V. This is where area is A. This is where area is small a, and velocity is say V dash. So we found V dash in terms of V by using equation of continuity, and we found out the expression of capital V. This one, this is what it is. And this is what we want to find out, at how fast the liquid is flowing in the main tube. So we can easily calculate the pressure difference P1 minus P2. That is going to be H rho G, where rho is, we can say rho M. Okay, so rho mgh is basically the pressure difference. Rho m is the mercury's density. So this is the formula that we derived last time. 2 times P1 minus P2 upon rho. Rho is basically the density of the liquid which is flowing here into capital A by small a square minus 1. This is in bracket. This was a very lengthy expression. I told you not to memorize this expression, rather apply Bernoulli's theorem and equation of continuity between these 2 points. The 2 points were point number 1 and point number 2. Okay, cool. After that, we spoke about a few applications of Bernoulli's theorem, more applications, and that is where I explained you how the rooftop of usually the huts in villages, when a very strong wind is blowing, it goes off because of Bernoulli's theorem. Always remember, whenever there is a high velocity at a given part of anything, like if we speak about the dynamic lift of an aeroplane. So the design of the aeroplane wing is such that when the air will flow, it will flow faster here. V1 will be more in comparison to V2. The design is such. Okay. So because of that, the pressure at 1 is going to be less than pressure at 2. Okay. We explained all of these things very much in detail. Because of that, there is a pressure difference, and overall the pressure difference creates a force F, which is upwards. Because of that, it takes a lift. Okay. So everybody, let's do a question based upon Venturi meter, velocity of efflux, and then we'll move to the real fluids discussion today. Today's our discussion will mostly be about viscosity, which is basically the friction in fluids, and then we'll speak about something called as terminal velocity. So as and when we reach there, I'll explain you that part also. So before we go to start the today's session, let's quickly start looking at this question and try to answer this. So guys, the question is, we have this container in which the liquid is filled to a height of 3 meters. So you create a hole, which we do not know at what level you have created it, but the base of this container is at a height of 1 meter. Okay, so basically the bottommost layer is at a height 1 meter, the topmost layer is at a height of 4 meters, you can say that, from the ground, and maybe at a height y you have created from the base of the container, you have created the hole at y. So you can say that this remaining distance is going to be 3 minus y. So the question is asking us that what should be the height of the hole that you are making here, so that the water can be sprayed up to maximum horizontal distance on ground. So when the water comes out, it goes to the maximum distance r. So you know that this r can be written as 2 times 3 minus y into y, but y plus 1, because there is additional height of 1 meter below y value also. So this is the range formula. I'm directly providing you this. All of you listen very carefully. Okay, where is it coming from? This is coming from here. This is where it is coming from. 2 times h minus h into small h in bracket, under root. So this is 2 times 3 minus y into y plus 1. This total height, y plus 1. Okay, so you have to maximize it, and for maximizing, you have to find the value of dr by dy, equate it to 0. Whatever the value that you get as the value of y, that is going to be the maximum value of y. Okay, that is going to be the value of y for which r is going to be maximum. Okay, giving you all 90 seconds for this, everybody. I hope you all remember how to differentiate, and the time starts in 3, 2, and 1. Last 5 seconds. Come on, everybody. Okay, that's nice. Okay, very good. So let's see. The correct answer to the question is 2 meters from the ground. That is option D. And let's see how this happens. We are going to differentiate this value. Okay, this is 2. Velocity of E plus is going to be 2g 3 minus h. We all know that. And r is going to be 2 h plus 1 3 minus h in under root. This is the part that I gave you guys already. Right? This is the part which I told you already. 3 2 into 3 minus 5 y plus 1. So let me just do it for all of you here separately. Okay, so we said that r is going to be 2 times 3 minus y into y plus 1 in under root. Okay, if you want to multiply things inside also, so this is going to be 3y plus 3 minus y square minus y in under root. That is going to be, by the way, 3 plus 2y minus y square in under root. This is how it is. So now when we are going to differentiate dr by dy, I hope that you people still remember some of that. So first of all, you can write this as power half. So chain rule. How many of you still remember Sholey theory? Sholey theory याद है? आज उसका यूज होगा बहुत दिनों के बाद में. After a long time, Sholey theory exactly, right? So let's see how it is applied. Okay, if you remember chain rule shortcut, that's what Sholey theory is. 2 remains as it is. You're going to first differentiate things which are inside. So differentiation of 3 is 0, differentiation of 2y is 2, differentiation of y square is 2y, and then forget about everything which is inside the bracket. Look at the bracket. So bracket to the power half. So the differentiation is going to be half bracket to the power half minus 1, and everything inside remains the same. That means everything inside is going to be 3 plus 2y minus y square like this. Okay, and this has to be equated to 0. So if you write it properly, this is how it looks like, by the way. Before you even equate it to 0, you can write it as 2 taken common, 1 minus y divided by 3 plus 2y minus y square power half. Why? Because this power is minus half. That means power will be, when the term will be brought to denominator, it can become positive power again. So when you equate this thing to with 0, okay, this is dr by dy. This entire thing goes multiplies here with 0. So you can see very clearly that 1 minus y is equal to 0. That's the only possibility. So y becomes 1 meter. But that cannot be the answer, because you're looking at either from the ground or from the base of the tank. So from the base of the tank, y value has come out to be 1, so it is not 1.5 for sure. So that's not your answer. So what you're looking for? Okay, so this is 1 meter. This was y. So you can say that y plus 1, that is 2 meters, is your answer from the ground, from the base of the ground. Okay, everyone. So this is what the correct answer is. Okay, good, everybody. So let's move on and begin our today's discussion. We'll be speaking about something called as viscosity, and we'll be speaking about Stokes' law and something called as terminal velocity. I remember, I think Irfan or Arshad, one of these guys asked me last time that, sir, when the raindrops fall, they are falling from such a long, such a great height. So by the time they are reaching the ground, their velocity should become so enormous that whichever body they are going to come in contact with, they should damage it. So if we go out and we are going and we are getting wet in water in the rain, then it should actually kill us. It should be so massive velocity, so huge value of velocity that eventually when that comes to our head and hits us, it should actually damage our body. So we'll understand why that does not happen in this topic today. That is called as terminal velocity. So wait and watch. This is going to be a very interesting discussion about the terminal speed. Okay. Before that, let's start the discussion of viscosity. Let me ask you people, what do you guys think viscosity is? Have you ever heard about viscosity or any general idea what exactly viscosity is? Okay, tell me. Resistance. Okay. Honey. Okay. Exactly. Perfect. It's basically friction in fluids. Can we assume that liquids, when they travel, they travel in the form of layers? They travel in the form of layers. We can say that. So basically, different layers placed over each other, they are going to definitely offer resistance to each other. We can say that. So if this is one of the layers, then comes the other layer. Okay, then comes the other layer. So maybe this is some oil which is spilled on the floor. This is what is representing the layers of oil which is spilled on the floor. So everyone, say this is our ground level, or this is where the floor is. As I'm moving up, what should happen to the velocity of the layers? What should happen to the velocity of the layers? The topmost layer, should it move easy or should it move a little difficult? The topmost layer, will it be easiest for it to travel or will it be most difficult for it to travel? Now, if you are not able to visualize this part, common sense part is still not developed with respect to this one. Think of these layers as different blocks of mass M1, M2, M3, and M4. Which block is easiest to move? Which block is easiest to move? The topmost one, right? So that layer can move very easily. Getting it, everyone? Because as you will go down, the weight of the upper blocks will increase the friction and will become very difficult to make the bottommost plane move. Getting it, everyone? It will become very difficult for the bottommost layer to travel because it has carried so much of weight above it that the friction is also increasing. Right? So this is the basic way of visualizing this thing. Okay? Absolutely. Right, everyone? Is that clear to everybody? Why the topmost layer will move relatively easily comparative to the bottommost one? Right? Great. Okay, great, nice. Okay. What makes a thick substance like honey to go with difficulty? Can anybody answer this question based upon what we know so far? This is the reason, Manav Verma, that the reason for liquids like honey, oil, to travel relatively with more difficulty comparative to water, the reason is viscosity. Viscous force, absolutely. And that is what we are going to explain today. That is what we are going to get into the depth of today. Okay. Is that clear? Cool. Okay. Now, for those people who are thinking that how there are different layers, so if you have ever been to, say, a beaches where sea water comes in, even the sea water comes in the form of layers. When the sea water reaches the banks of the land, that is where you can actually visibly see there are different layers being formed. You can consider them to be like the waves, okay, but not exactly crust and trough waves, but they are layers over each other which are traveling, and that is how liquid is imagined to be traveling, and that's how it moves. Okay, everyone understands now? Good, cool, awesome. Yes, sure. So is it laminar flow? So basically, we are in our discussion assuming that things are going laminar only. Okay, Darshan. So everybody, viscosity technically is defined as the internal resistance offered by a layer of fluid to the adjacent layer during the fluid flow. Simple. So all the layers will try to resist the adjacent layer's motion. They will hinder the motion of the next layer. So if you have, say, the one that we saw just now was this one. When you have multiple layers placed in such a way that when I'm placing layer by layer, we have the topmost layer more or less like a free layer. Or you can say you are placing these multiple layers between two glass slabs. So you can read this also. Fluid film between two glass plates. Okay, so between two glass plates, if there is some liquid which is filled and the bottommost layer is not allowed to move, then the topmost layer, as we know, it's easiest for it to travel. So it will take the glass slab at the top also along with it, like that. So guys, there is one important point that we need to look at in the two diagrams that we see here. The first one is the side view. All both of these are the side views, by the way. Say when the water is spilled on a floor, the way it is going to move, the topmost layer will move very easily, and the bottommost will move with most difficulty. That's the first one. This is the first one. When the liquid is allowed to move on a floor, kind of that kind of situation. Here they are talking about two glass slab between which the liquid is placed, but more or less what they mean is this thing. The second one is basically like liquid traveling in the form of cylindrical layers in a pipe. Means what? If you look at it from here, this is how the liquid will appear to you. Not actually, but this is how you will visualize it, the layers. Okay, so these are the different layers which are getting created when the liquid is traveling inside a pipe. Okay, everyone. So innermost is 1, then 2, then 3, then 4, then 5, like that. So this is 1, then 2, then 3, then 4, then 5, then 6. Similarly, this is 2, 3, 4, 5, 6. Are you guys able to visualize this? The side view and the front view, right, everyone? So this is the front view. So do you guys see that it will be easiest for the central layer to travel now when we are speaking about the motion in a pipe? Because the boundaries of the pipe, they will create relatively different friction, which we will understand later on, or we already may be aware about this, something called as adhesive forces. So they will create more friction, more resistance, because of which the layer which is inside, which is getting least affected by the solid surface, is going to travel with the maximum ease. So this is the fluid flow in a pipe. Yes, cohesive and adhesive forces. Adhesive forces are the forces which act between different materials. So liquid is one material, maybe your plastic pipe is the other material. Okay. Yes. So Lisa Biswas, definitely layers are under the pressure of different layers also, definitely. Okay. Are we clear so far? Everybody with me? Okay, very nice, thank you. So let's then why isn't. So that is what I said. Here, this is solid surface. Here, it is liquid surface. Okay. So ideally, if the solid surface would not be there, this is solid. Okay. Then the liquid will not be able to travel in this form in a pipe. The liquid will not be able to travel in that form. So definitely you require a pipe kind of body in which the liquid will travel. So what happens when liquid comes in contact with another material? Okay, that is usually a solid. So these are two different nature of materials. So the type of force which act between two materials of different nature, that is called as adhesive force. Okay, so usually these adhesive forces are stronger in comparison to cohesive force. Not necessarily all the time, but in most of the cases, when we speak about a liquid and a solid body coming in contact, usually oil, water, sanitizer, you will always find the central part moving relatively faster in a tube, because the boundary layer which is coming in contact with the pipe body, that is experiencing adhesive force. So that is offering more resistance to the liquid flow. Okay. Okay. Sir, honey moves slow than water due to viscosity. Then how water moves faster than honey? But you are first explaining the same point and then you are contradicting the same point, or you are rather asking the same question once again. If Usain Bolt runs faster than Milkha Singh because he is fast, then why Milkha Singh runs slower than Usain Bolt? This is what you're asking. If honey moves slow because of viscosity, that simply means the viscosity in honey is more in comparison to water. It's like because Pakistan won the match yesterday because they played well, then why did India lose? It's like that. Because we did not play that well. दिल पे लगेगा तो समझ में आएगा. Okay. Shall we continue, everybody? We'll keep like 2 minutes silence at the end of the class. Okay? Not now. Now I'll rather keep the entire class silent for the entire explanation of this from henceforth. Everybody, let's get back here. Hello? विष्णु जी, हेलो, आवाज आ रही है मेरी? Can you hear me? Okay. कौन सा वाला पार्ट, इसमें से कौन सा वाला डायग्राम डिफिकल्ट है विजुलाइज करने को? क्या बोल रहे हो? यार ये पाइप ऐसा मान लो, यहाँ से वाटर फ्लो करके जा रहा है, तो ये अलग अलग सिलिंड्रिकल लेयर्स के फॉर्म में वाटर ट्रैवल कर रहा है. ये विजुलाइज कर पाना पॉसिबल है? तो मैं उसको सामने से देखूंगा तो ऐसा दिखेगा ये वाला डायग्राम, और साइड से देखूंगा तो मुझे डेफिनेटली सिर्फ साइड में तो ऐसा दिखाई देगा ना, जैसा भी डायग्राम में दिखा है. पक्का? तो ये वाली जो सेंट्रल लेयर है ना, जिसको अभी मैंने ब्लैक कलर से कलर कर दिया पूरा, उसको सबसे कम रेजिस्टेंस मिल रहा है, बिकॉज बाकी की लेयर्स जो है उनके ऊपर सॉलिड का इफेक्ट पास ऑन होकर क्या है. तो ये वाली जो पहली लेयर नंबर 6 जो दिखाई देती है, दिस लेयर नंबर 6 एक्सपीरियंसेस मैक्सिमम रेजिस्टेंस फ्रॉम द सॉलिड बिकॉज ऑफ समथिंग कॉल्ड एज एडहेसिव फोर्स. ओके. उसके बाद what happens, the layer 6 will transfer some amount of that resistance which is experienced by it to layer number 5, but not as much as it itself is experiencing. So 5 will move little faster than 6. Similarly, 4 will move even faster, 3 will move even faster, 4, 3, 2, and finally 1. The central layer in this case will move fastest. Is that clear? Cool. Yeah. Okay, everybody. So one thing that I need to mention here to all of you guys, say if we speak about any layer which is moving with a velocity v, okay, maybe this layer is moving with a velocity v, and if you move up, say by a distance delta x, the velocity also increases by v plus delta v. Means it becomes v plus delta v as you move up by a height delta x. So we define something called as delta v by delta x, which we call as velocity gradient. Means what? As we move from one layer to another, how much change per unit height or per unit change in the height of the layers is coming in the velocity is what we call as velocity gradient. And during laminar flow, the discussion that we will have, usually this value of change in velocity upon change in height, which we are calling as velocity gradient, usually this value will be considered to be almost a constant. That is when this profile will look like this. Means if you will look at it very carefully, this is going to relate to this angle theta, right? So if different layers are moving, means what I'm trying to tell you guys is, if this velocity is 2 meters, and if we say go to the next layer and that moves with 3 meters per second, this one is moving with 2 meters per second. So on a movement by 1 centimeter up or 1 millimeter up, if the layer 1 millimeter above increases its velocity by 3, then after 1 more millimeter if I go up, okay, then the next layer must move with a velocity of 4, so that this change in velocity upon change in height should remain a constant. Okay, everyone. So we are calling this part as velocity gradient. Okay, so the force which acts between the layers when they are traveling, it is defined to be proportional, or rather it is practically found to be proportional to the area to which the liquid layers are spread off. So unlike solids, in liquids, more be the spreading of the liquid, more difficult it becomes for the liquid to travel. Okay, so it is proportional to the area of cross section of each layer. Okay, don't get confused with this capital A. We are talking about how much the liquid is spread over a surface, right? So the more be the spreading of that liquid, the more it becomes difficult for the liquid to travel. Okay. Secondly, it is directly proportional to dV by dx. That means what, guys? If, say, by movement of 1 millimeter, I'm checking every 1 millimeter movement upward, if I check the amount of velocity by which the value is changing, we can say that more be this change per unit length that I move up, more be this change, that is a measure of amount of force which is acting between the two layers. As we are moving down, we are sure that the force of friction is increasing. That is why it is becoming difficult for the layers to travel. So if we find that by moving 1 millimeter in water, if we are moving 1 millimeter down every time, the amount of change in the layers of the velocities, or the layer velocities, will be relatively less in comparison to honey. In honey, you will find that gradient to be very steep. Means what? You will find that layers are finding it very, very, very difficult as you keep on going down. That actually is the measure of the velocity gradient. So more be the value of velocity gradient, more frequently or more faster the velocity is changing as I move from one layer to another. And that is itself is a sign of high viscosity or high viscous force. Okay, guys? So when we put them together, there will be two different liquids in which you may have same value of area, same value of dV by dx, but still you will not find the similar viscosity in them, because, or other viscous force in them, because the nature of the liquid also will play a role. Means what? Maybe I'm going to create a situation where I'm spreading water and honey to the same container, so the area of cross section becomes the same. Okay. Secondly, I might by any means, by maybe trying to keep it with respect to varying the temperature or something, I'm still able to manage the same value of velocity gradient also. But we know that water fundamentally is less viscous in comparison to honey. So the viscous force in water will any which way always come out to be lesser in comparison to honey. So that is where, when we remove the proportionality, we bring a constant of the nature of the liquid that we are dealing with. And that is what we call as the coefficient of viscosity, which stands parallel to coefficient of friction, by the way. Means what? Similar kind of role it is going to play. This is something which is going to talk about the nature of the liquid that you are dealing with, how difficult it is for that liquid to travel. It is directly measure of that. Means wherever we spoke about coefficient of friction earlier in laws of motion, we realize that more be the value of mu, that means coefficient of friction, more difficult it is for the two layers to move with respect to each other. Similar role is here of coefficient of viscosity. More is the value of coefficient of viscosity, more difficult it is to have an inter layer movement. Okay, how do we pronounce this symbol? This symbol is pronounced as eta. Okay, this symbol eta. It's like writing n and elongating the length of one of its sides. So eta is what we call it. Okay, and this is what we call as coefficient of viscosity. This is an important formula. By the way, guys, this formula in books you will also find a minus sign here. That minus sign indicates the resistive nature of the force. That means it is opposite to the direction of flow of the layers. That is where. So opposite to the direction of relative motion. That is what it indicates. If you find a negative sign in the books. So the formula's expression matters. Eta a dV by dx. Eta is coefficient of viscosity. A is the surface area of layer. Okay, surface areas of the layer. dV by dx I've already told you is the velocity gradient, and force is the viscous force which is acting between different layers here. Okay, how do we measure viscosity? The units we actually find that out. It comes out to be Newton second per meter square. Okay, everyone. If we find the units of eta, eta's unit actually come out to be Newton second per meter square, and also called as Pascal seconds. But many times in this chapter you will be dealing with CGS unit of this quantity, CGS unit, yes, which is called as Poiseuille, or in short it's called as Poise. Again, after the name of the scientist whose equation we are going to study after some time. Okay, Poiseuille or Poise is the CGS unit. Remember this conversion in SI unit, it is 1 Pascal second, which is equal to 0.1 Poise. So Poise is basically the bigger unit. You can say that. Dimensions from here you can find out m1, l minus 1, t minus 1. That's going to be the dimensions of this quantity. Okay, everyone, please remember the SI unit is Pascal second. The CGS unit is Poiseuille, or in short it is also written as Poise, P-O-I-S-E. Okay, everybody, everyone has noted down this formula, the viscous force formula between the two layers. Confirm in the chat box. Very good, great. Remember this conversion also, everybody. 1 Pascal second is 0.1 Poiseuille. Okay, everybody. Yes, so let's look at some examples and a few questions. Okay, everybody. Okay, so this question, it says that the space between two plates area is given to us as 20 into 20, and it's the gap between the two plates is given to us as 1 centimeter. Okay, so they are filled with a liquid of viscosity 1 Poise. So CGS unit, the value is given. The upper plate is dragged to the right with a force of 5 Newton. So definitely the topmost layer of the liquid also is going to move with the same force. Okay, so keeping the lower plate stationary, if you're able to do this, then you're creating a velocity gradient, by the way. So what will be the velocity at the middle of the plate? Okay, so you are trying to find out the velocity of the middle layer over here. So there will be a middle layer. If we talk about its height, this height is 0.5 centimeter. How much is the velocity of this layer? We want to find out. Okay, everybody. So we want to find that out. We know the value of the force which is acting. We want to find out the value of this velocity. So we'll go by the formula only. F is equal to eta a delta v by delta x for this one, assuming that this one has 0 velocity. So v by x delta v by delta x. So v by x we can say the initial or the bottommost layer has 0 velocity. So we'll find that value accordingly. Okay. So as long as the velocity gradient is same, whatever force is experienced by this layer will also be experienced by the middle layer, will also be experienced by the bottommost layer, as long as we are assuming that the velocity gradient is constant. Okay. So everybody have a look. eta a v by x is what we're simplifying. We want to find out the value of v here. Force acting on all the layers is assumed to be 5 into 10 to the power 5. Okay, multiplied by the value of x, which is this gap, that is 0.5. This gap is also equal to 0.5 centimeter. Okay, the value of eta, I'm putting it. By the way, if you will notice, I'm simplifying the question in CGS unit. So I've converted the force, which is given to us as 5 Newton. We can write it as 5 into 10 to the power 5 dynes. And rest all the values are already given in CGS unit. So force is 5 into 10 to the power 5 dynes. The value of this distance is 0.5 centimeters. The value of eta is already 1 poise. And the value of this area is 20 into 20, 400 centimeters square. So just writing it in CGS unit only. Everything set. Squaring this value, simplifying this value. So this 0.5, one decimal can take care of this one of the zeros. So 5 into 5, 25, 10 to the power minus 5 into 10 to the power minus 1 becomes 10 to the power 4 divided by 400. So we can say 25 by 4 into 100. Okay. So 25 by 4 is 6.25. We already know this, multiplied by 100. And the answer is definitely in centimeters per second because we are solving the question in CGS unit. But if you look at the options, they are in meters per second. So now we can again convert our answer back into the SI unit system. So this 100 centimeters per second can be written as 1 meter per second. So 6.25 into 1 meters per second. This becomes our answer. Okay, everybody? Is it clear to everyone? Everyone understands this? Simple. The application of the formula is. Okay, that's great. Eta value is given to us 1 poise. That's why. So we have to put minus sign also. So actually, minus sign is only indicating the direction, as I told you. Okay. You can take it from. We have taken it from the bottom. We have taken it from bottom. Delta v by delta x is v minus 0 upon x minus 0. Okay. So we are finding x value is 0.5. Okay. We do not know the velocity of the topmost layer. We know the velocity of the bottommost layer is 0. Okay. Good. Nice. Cool. Awesome. Everyone, try to answer this question now. Question for all of you. The water flows between two plates. I'll get back to you, Lisa. I'm not understanding if you have a doubt. Water flows between two plates, of which the lower one is stationary and the upper one is moving with the velocity v. Okay, so the plates, the two plates, the bottommost plate is stationary, the topmost plate is moving with the velocity v. So what will be the velocity of the fluid which is in contact with the upper plate? What will be the velocity of the topmost layer of the liquid which is in contact with the topmost of the upper plate? Is what you have to comment on. Giving you 45 seconds and the time starts in 3, 2, and 1. Last 10 seconds, guys. Come on. Very nice. Remember, the layer of a liquid which is in contact with a solid, it's practically not going to move. It's almost stationary. And especially in this question, when they are saying that the bottommost plate is not moving, okay, and the lower layer of the liquid is also not moving, that means there is no relative motion between the solid plate and the layer of that liquid. So topmost layer, if it is moving with the velocity v, then the topmost layer of the liquid will also move with the same velocity v. Okay, so correct answer is v here. Okay. Lisa, I'm trying to unmute you. It's not working, I guess. Hello? Lisa, are you there? Yes, Lisa, I can hear you. No, I'm not. Eta value is 1. Area. No, it is given. It is given. 1 poise. Okay, and 400 is 20 into 20, the surface area. Got it? Okay, everybody. Now, a small topic once again, which we'll have to remember as it is. This basically, if you people remember, we spoke about the formula of rate of flow of liquid. When we were speaking about the ideal fluid, it came out to be simply A1 V1 equal to A2 V2. That's what we remembered. But when the real fluid is going to flow, the formula that we're going to remember, the equation that we'll remember is called as Poiseuille's formula or Poiseuille's equation. The name sounds like an Italian name once again. So some Italian guy. I haven't done the research. I'm not into trivia much. So the Poiseuille guy, he explained how the liquid travels per unit time, the volume of it, how much volume per unit time, okay, is going to flow through a given tube whose length is L, the radius is R, and the pressure difference between the two ends of the tube are given to us as P. So if this is basically, say you're talking about a pipe or a tube, its length is say L, its radius is R. Okay, and what else? The liquid which is flowing inside has coefficient of viscosity eta. So and basically there's a pressure difference obviously P1 and P2, definitely P1 greater than P2. So the pressure difference P1 minus P2 is either written as delta P or in this case in the formula it is written as small p. Only when there's a pressure difference the liquid will flow. Practically you have to create more pressure if you want the liquid to travel in this side. Okay, so the volume flow rate of the liquid under the pressure difference P, okay, is given as pi r to the power 4 into pressure difference upon 8 eta into L. This formula is known as the Poiseuille's equation or Poiseuille's formula. I want you people to remember it because we don't do the derivation of it in our JEE syllabus or in our board syllabus. Okay, so please remember this formula. Pi r to the power 4 p divided by 8 eta L. This is the volume flow rate formula that we talk about for a real fluid which is flowing in a pipe. Okay, just a second. Okay, guys. Everyone noted down the formula. Please remember that formula. Okay, I have told yes. I'm feeling a little sneezy today. No, I'm absolutely fine that way. Basically, रोए तो नहीं ना सर, अरे मैं कल बहुत रोया यार, इंडिया हार गया मतलब. तुम बार बार मुझे याद मत दिलाओ, लेकिन कल बहुत बुरा हुआ। अरे मैंने बाल्टियां भर दी कल, तब भर दिया मैंने आंसुओं से। ठीक है, चलो, we will not get carried away with this. We want to finish off today's discussion first, and then maybe we'll collectively will feel sad about it. Okay, but not now. In between, not in between. Chalo, everybody, let's have a look at a few examples based upon this equation. Okay, so that we remember the equation a bit. And the application is very straightforward. You have to find out the value of, in this case, you have to find out the value of the rate of flow. That means volume flow rate. Even the units are telling you that. Interesting thing to notice, guys, before even reading the formula, reading the question, that all the options are suggesting CGS unit system. So I will not even try to convert anything into SI unit system because the answer itself is in CGS. Question is asking me to find out the value of rate of flow of liquid. That means Q, and that I'm also trying to remember the formula. That says pi r to the power 4 into pressure difference, or you can just write down as P also, doesn't matter, divided by 8 eta L. That's the formula. So in the question, pi value we already know. R value is 1 millimeter. So obviously this 1 millimeter can be written as 0.1 centimeter. I cannot go with millimeter. That's not CGS. Excuse me. The length value is already given to me as in centimeters. Pressure, very good. It is given in times per centimeter square. Very good. Calculate the rate flow. If the coefficient of viscosity is 1.25 centipoise, like centimeter is 10 to the power minus 2 meter. So I don't want centipoise. I want poise. That means if I talk about eta, eta is 1.25 into 10 to the power minus 2 poise. So these are the values which are now good enough to be put in the formula to get the value. So the interesting part is the calculations are very simple here. If we put the value of pi, it is 3.14. The value of pressure difference is 10 to the power 4 in CGS. The value of R is 10 to the power minus 1. This is 0.1 centimeter or 10 to the power minus 1 centimeter. Power 4 becomes 10 to the power minus 4. So 10 to the power minus 4 and 10 to the power plus 4 cancels. You have in denominator 8 into eta into L. Eta I told you we convert it into poise. So 1.25 multiplied with 10 to the power minus 2 divided by 100 becomes 0.125 multiplied by 10. Interesting part. You multiply this with 10. This becomes 0.125. 0.125 multiplied by 8 comes out to be 1. You can do that yourself. So see that the denominator comes out to be 1. Numerator everything got cancelled. The value of rate of flow comes out to be pi centimeter cube per second. That's our answer. As simple as that is the calculation of this one. So very smartly they have given the values, and we were supposed to not convert anything into SI unit. So in this particular part of the chapter, we will keep an eye on the options also. If the options are suggesting that things can be solved in CGS unit system, we will try to keep it that way. Very rarely in physics we do that, by the way. Very rarely in physics we will do that. That you will find the question which will not require you to convert things into SI unit. Very rare. So that is why special one. Okay. Good. So we've got the answer 3.14 centimeter cube per second. That's our answer. Let's have a look at one more question which is on the similar lines. Again. Okay. 998. Poise itself is CGS unit. Everybody, poise itself is CGS unit. Centipoise is not CGS unit. Centi is a centi, kilo, mega, micro, nano. These are prefixes. These are prefixes. They can be used anywhere in any unit. So remember, centimeter is CGS unit of CGS unit of length. Okay, because you have meter as the SI unit. Okay. I do not know Munish. Okay, everyone. So pay attention. This one says that Munish, I think you'll have to Google that part and maybe we'll find that out. So this one, water is conveyed through a horizontal tube of 8 centimeter in diameter, so radius becomes 4 centimeter. And 4 kilometer in length. So obviously it won't work. Length has to be 4 into 10 to the power 3 meters or 4,000 meters. The rate at which the liquid is going, V by T or Q, is 20 into 10 to the power minus 3 meter cube per second. If I'm converting everything into the unit system, this is going to become everything in SI unit. So liter is not supposed to be used. In fact, liter is not even CGS unit. So you'll have to use 20 into 10 to the power minus 3 meter cube per second. In physics, we don't use it in liters at all. Okay, and we have to calculate the pressure required to maintain the flow. Coefficient of viscosity, eta value is also given in SI units only. So eta is 10 to the power minus 3 Pascal second. We are trying to find out the value of P. So once again, if we speak about Q, which is pi r to the power 4 P by 8 eta L, this is what we are this time interested in finding. Okay, so everybody, we have everything given to us. P on rearranging the formula becomes 8 eta q L by pi r to the power 4. 8 into eta value into q value, as I told you, will multiply by 10 to the power minus 3. L value 4,000 meters. The value of pi, the value of radius 4 into 10 to the power minus 2 power 4. So when we do the math, obviously a lengthy calculation, it is going to be the pressure value will come out to be close to 8 into 10 to the power 4, or precisely 7.96 into 10 to the power 4 Newton per meter square. Okay, again looking at the options, we had to work with the SI unit system here. Okay, good, nice. Okay, everybody, question for you people to try. It's going to be an easy one. Have a look. So we have two tubes or two pipes of radii R1 and R2. Their lengths are also L1 and L2, and they're connected in series. Okay, and liquid flows through each of them in streamline conditions. And when we say streamline condition, basically the rate of flow, the amount of liquid entering and the amount of liquid exiting has to remain the same. Okay, per unit time. So Q1 is equal to Q2. P1 and T2 are the pressure differences across the two tubes. The two tubes, the left side tube is P1 pressure difference, right side tube has P2 pressure difference, and it is also given that pressure difference P2 is 4 times the pressure difference P1. Please don't think that it is pressure at one of the ends. So there are basically two tubes with different areas, something of this sort you can say. So here the pressure difference is P1 and here the pressure difference is P2. So P2 is 4 times P1. This is L2, this is L1, and L2 is also 1/4 of L1. That's what is given. You have to talk about the radius R2 in terms of R1. What is going to be the relation? They have the same value of rate of flow of liquid. Giving you people 90 seconds, and the time starts in 3, 2, and 1. Come on, people. 10 seconds more. Okay, so this should have been easy for everyone to do. And why? If you have this formula Q as pi r4 p upon 8 eta L, same liquid is flowing, so definitely eta is same, 8 and pi are anyway constant. So you're saying that Q1 is equal to Q2. So we can say that R1 to the power 4 P1 by L1 is going to be R2 to the power 4 P2 upon L2. Correct. So we can say that R2 to the power 4 P2 I can write as 4 times P1. L2 I can write as 4 times L1, L1 by 4, or I will keep L2 as it is. I'm keeping L2 as it is. Okay, everyone. So R1 to the power 4, this is P1. I'm converting L1. Okay, I'm converting L1 in terms of L2, calling it as 4 times of L2. Make sense to everyone so far? Right? So P1 cancelled, L1 cancelled. What do I see here? I see that R2 to the power 4 is R1 to the power 4 by 16. That's what it is, correct? Which we can say is R1 to the power 2 to the power 4. Right, everybody? So R2 is half of R1. Easy it was? Great, nice. Okay, everybody. Absolutely, radius has to be small. Chalo, everyone, moving on to the next half of the session. That is where we'll speak about something called as Stokes law and not Ben Stokes. Okay, let's not relate everything with cricket. So Stokes law and something called as terminal speed. We'll speak about that. Now, again, Stokes law is even if you will go and refer your NCRT, the formula is not derived. It is rather derived from dimensional analysis. Yes, it is derived using dimensional analysis. So if you want, you can do the derivation also, but by using the dimensional analysis. What exactly Stokes law speaks about? It says that if you conduct an experiment in which you take a container, you fill a viscous liquid in it. Okay, you fill a viscous liquid inside, whose viscosity is eta. And then you take, say, a spherical ball, small marble maybe, and you start making it fall down because of the gravity. So as this falls down, its velocity definitely will change. So as it moves in the container, it definitely is going to experience a viscous force, which we call as the viscous drag. This viscous drag force is directly proportional to the value of coefficient of viscosity of the liquid, obviously. It is proportional to the radius of the spherical ball and velocity of the liquid, of the body, which is trying to move inside this liquid column. So when we remove the proportionality which is found experimentally, this formula is what we get. It comes out to be 6 pi, the proportionality constant, okay, and eta into r into b. You can try doing this by using dimensional analysis. You'll get the value of these three powers as 1 only. Okay. So everyone, this is the formula of the viscous drag which is experienced by a solid body. See the first formula that we found out, or we wrote, this one. This formula that we wrote. This was the viscous force experienced by one layer because of the other layer of the liquid. This is the inter-layer friction force between two layers of the liquid. But if a solid body is trying to move inside a liquid, which is viscous, this is the force which is experienced by the solid body when it tries to move inside the liquid. Okay, the experiment is conducted or was conducted with the help of spherical bodies. That is why the formula has r, which is the radius of the spherical ball. Okay, what is important to remember and to understand that unlike your kinetic friction force, which used to be a constant on a given surface, your viscous drag force or viscous force is directly proportional to the velocity of the solid body, and that's a huge breakthrough in the mechanics itself. Why? Because more fast your body tries to move in the liquid, more difficult it becomes for the liquid to travel, for the body to travel. Okay. In fact, everybody, that is the reason when meteors enter into atmosphere of any planet, say on Earth, when the meteors enter in the atmosphere, they experience, first of all, they're moving at a very high velocity. Okay. They move with very high velocity, and when they enter into the atmosphere with that high velocity, because of that high velocity, a very strong viscous force starts acting on them, and that is why that viscous force, when it starts doing the retarding force, start doing the work, the non-conservative force of viscous force, when it is working, it tries to decrease the mechanical energy of the meteors. And eventually, what happens to the meteors when they enter in the atmosphere? May I know? What happens to the meteors when they enter in the atmosphere? They start burning out. They start burning out because of this reason. They burn because of the work which is done by the viscous force, and they eventually slow down. Most of the time, before even reaching to any point significant on Earth, they burn out completely. Okay? Yes. And because the formula was, this formula is valid for any fluid. This formula is valid for any fluid, any real fluid, including air. Okay. Okay, everybody. Wow, question of the day. The question of the chapter. Answer, everybody. Is air a fluid? Now that reminds, or rather that puts me into a situation to ask you people, what is the definition of a fluid? What is the definition of a fluid? Come on, everyone, tell me. Anything which can flow. Can air flow? Daksh Chaudhary, do we have your answer, or do you have your answer now? अपूर्व एक क्रिकेट की बॉल लेते हैं और उसको जला देते हैं और वो ना बुर्ज खलीफा टावर से ड्रॉप कर देते हैं। बुर्ज खलीफा मालूम है ना, टॉलेस्ट टावर, ठीक है। तो जब उसे ड्रॉप करेंगे तो ऐसा हो सकता है कि बिफोर हिटिंग द ग्राउंड पूरी जल जाए, पूरी उसमें कन्वर्ट हो जाए और अर्थ तक आते कुछ इंपैक्ट ही ना हो, ठीक है। लेकिन अब अगर मान लो हम उसकी जगह एक कॉर्क वाली बॉल ले लेते हैं, मतलब और भी सॉलिड मटेरियल की बॉल ले लेते हैं और उसे जला देते हैं और उसे ड्रॉप कर देते हैं, तो जरूरी नहीं है ना कि वो भी कंप्लीटली एशेस में कन्वर्ट हो जाए। तो अब जब अर्थ गिरेगी तो जाके कुछ ना कुछ तो स्ट्राइक करेगी। Same can happen with the meteor. Depends on the size and the mass of the meteor. It may be completely burnt out, may not be completely burnt out. That depends on a lot many factors other than the viscous force. Okay. Okay. We will आराम से 2 मिनट रुक जाओ, बात करते हैं. So सबको ये बात समझ में आ चुकी है, सबने फॉर्मूला नोट डाउन कर लिया, everybody has done this formula, first we'll see the application of this. Very important is to remember this, that your viscous force is directly proportional to the velocity with which the object is trying to move. And that is why when you try, say when there is a very, very windy day, it's like super duper fast wind is blowing outside. If you're just standing on the road, it may hit you and you will feel the force. But you try to run in that wind, or if you try to do cycling in that wind, you will find that running and cycling becomes even more difficult on a windy day comparative to just remain standing, because you are gaining velocity. And when you try to gain velocity, the viscous force of air will also become stronger on you. That is the entire scenario of viscous force. Okay, yes, you know the struggle of cycling. That is great. Okay, sir, meteors burn after entering Earth's atmosphere. Are you asking or are you telling me, Harshan? Obviously they burn, यार. ठीक है, चलो अभी मेरा रोस्ट करने का मूड नहीं है. ठीक है, yes. चलो everybody, let's have a look at a few questions based upon this. A raindrop of radius 0.3 millimeter falls through air with a velocity of 1 meter per second. The viscosity of air is given to us. That means eta value is given. Find the viscous force on the raindrop. That means we want to find out F, which is equal to 6 pi eta RV. We have been given the value of eta. Achha, options are all in dynes. That means I don't need to convert anything into SI unit. So I'll rather convert this into centimeters. So 0.03 centimeters. Velocity is going to be 100 centimeter per second, and this is already in poise. So this is 6 into 3.14 into 18 into 10 to the power minus 5 into 3 into 10 to the power minus 2 centimeter, and velocity 10 to the power 2 centimeters per second. So this gets cancelled. I will have 6 3s are 18 into 18 into 3.14 into 10 to the power minus 5. Okay, so when we do the maths, obviously I'm not doing that maths, we'll get the value as close to 1 into 10 to the power minus 2 times. That's option B. Okay, everyone. So we converted everything in the form of CGS units and then just simplified it as what the value demanded as per the options, obviously. Okay, everyone. Next one is going to be a question that you guys will have to answer. Okay, I will set that question as a quiz. Just a second, please. Okay. Okay, everybody. So question is, what happens to the drag force on a sphere if radius is increased by 50%? I think Kostov asked me, sir, is this formula that we are writing 6 pi eta RV, is it valid only for spherical bodies or is it not valid for non-spherical bodies or what? So the formula that we have right now in front of us can be applied for spherical bodies, but viscous force acts on everything. Viscous force acts on everything which tries to move in a fluid. Okay, but you will not be able to apply that formula because of the part that it is done experimentally for spherical bodies. That's why. So everyone, question is asking us, if this radius of the spherical ball which is falling inside, if we take another ball whose radius is 50% more, then what happens to the viscous force on that new body, on new ball? Giving you guys say 60 seconds for this, and the time starts in 3, 2, and 1. Okay. Okay. Oh my god. 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 If radius is increased by 50%, just tell me, if radius is increased by 50%, R will become how much? Will it be 1.5 R or not? Is there anybody in the class who does not understand this? Wrongly tagged. Correct answer is option C, by the way, everyone. Okay, then it's my mistake, not your mistake. Then it's my mistake. Okay, then it's my mistake. ये लो, सभी लोग. हाँ. I agree with all of you. I agree with all of you. Okay, correct. The answer is option C. Okay, I think by mistake I have incorrectly taken yes. Yes. No problem. It's okay. Don't thumb down the slide, guys. There is no mistake. The correct answer is option C only. Okay, everyone. Okay, Shika, I would understand that. So anyway, everyone. So if you look at this, that radius, if we increase the radius by 50%, then definitely R value becomes R plus 50 by 100 R, which is 1.5 R. And you can see that viscous force is directly proportional to R. So F will also become 1.5 F. That means correct answer is going to be option C. Okay. So sorry guys, I'm still recovering from the shock that I had yesterday. You know what shock, right? Anyway, so guys, let's speak about something called as the terminal velocity. Okay. This is the last topic of today. Then we'll have many questions to solve based upon the same. Tell me everything. Tell me everybody, when anything which falls in a fluid, anything which falls in a fluid, what is the downward force that acts on the body when it's falling free fall? Definitely mg is acting. Everyone agrees. Any upward force which will act on it? Any upward force that will act on it? Archimedes, Baba Archimedes. Buoyancy should act or not? Air is a fluid or not? Definitely, right? And now because your body is falling downward with a velocity v, should there be one more force upward in a real fluid or in the opposite direction of the motion? Viscous force, correct? Now, as air is filled everywhere when a body is falling downward, pay attention and answer me accordingly. Can I say mg is almost a constant near Earth's surface? Mg is almost a constant near Earth's surface. 9.8 के आसपास value है. Can I say buoyant force is always going to be constant in that case because body is completely submerged in air, completely submerged? But what about this force, viscous force? Is it constant? Is it constant? No, it is not constant. Rather, it is dependent upon the velocity. So initially, as the body is falling downward, its velocity will increase as you drop anything. Just imagine people who skydive, people who do skydiving, when they start falling, parachute to question me, we're not even talking about parachute. When they are falling freely, their velocity is increasing, and as the velocity increases, can I say that this viscous force is also increasing? Right? So guys, tell me one thing. Can I say that if there is sufficient height for the body to fall, there definitely would come a point when viscous force plus buoyant force will be able to balance mg? Is there a possibility or not? Theoretically, there exists a possibility, right? And this is what happens with raindrops. This is what happens with raindrops, that they achieve a constant velocity and they do not accelerate further. And because their mass is not very high, they achieve that velocity very fast. Because of that, when they fall on Earth, they fall with a constant velocity, which is not so high that they can damage things on which they are falling. Okay, let's see this animation. I hope this helps you a bit to understand. Very slow animation it is, everyone. When that thing is falling down, look at the upward air resistance force. Look at the upward air resistance force and the net force also. Keep an eye on this also. See what is happening. Okay, keep an eye on the force. Everyone is able to see the animation here? Everybody, right? So see that the net force is almost becoming zero in that case. This is the situation. Okay, everybody, this is the situation where we can say that the body has achieved a constant velocity. This is the situation where acceleration will become zero. Okay, this is the situation where acceleration becomes zero. Net force acting on the body becomes zero. Yes. Okay, and the velocity of the body becomes a constant. Okay. CT is not present, no problem, guys. I'm there. Don't worry. Okay, so this constant velocity is what we call as the terminal velocity. Is the logic clear first of all? How the body is achieving a constant velocity? Because this air resistance is directly proportional to the velocity of the body. Okay. Okay. Now the idea is clear or not? Now the velocity becomes constant. अरे GIF है ही नहीं अभी सामने. This is simply a slide. It's not a GIF. It's a slide. It's an image in front of you right now. I'll rejoin the class, everybody. Okay, everyone. Is it fine for everybody now? Okay, good. Yes. Can this be called equilibrium? Nihal is asking. What others say? Can you call this situation equilibrium when the body is moving, but the net force acting on it is zero? The body is still moving, by the way. It is still moving with a velocity v, but that's a constant. Can we call it equilibrium? Yes, we call it equilibrium. And that is why in laws of motion, the first law says that a body which is in the state of rest or in the form of uniform motion will remain in that state until unless there is a non-zero force acting on it. Okay? Cool. Air resistance is the viscous force, absolutely. In vacuum, terminal velocity isn't present. In vacuum, there cannot be the case of terminal velocity. The body will eternally accelerate. If there would be no atmosphere, then definitely raindrops will kill us. But in that case, your clouds may not even survive. They will not even be formed if there is no atmosphere. Clouds ही नहीं होंगे. Okay, anyway. चलो बाद में बातें करेंगे. Everybody, let's focus on this last slide of theory. Then we have only problems coming up. Yes, so everyone, imagine the raindrops to be spherical, having a density of rho s. Okay, rho s is basically telling us a solid body's density. Okay, so assuming any solid body whose density is rho s, its weight will be equal to mass into mg basically. So mg is written as density into volume into g. So that's its weights. The buoyancy force is rho into v into g, and this rho is basically the density of the liquid, by the way. Rho L is the density of the liquid, and 6 pi eta rv is the viscous force. So we say that at equilibrium, the body achieves the terminal velocity. Okay, that velocity is what we are interested in finding. So we say that the downward force should be equal to the total upward force. So downward force is mg equal to the buoyant force plus viscous force. Okay, the first equation is clear to everyone. This is the key equation to understand the derivation here. Right? So see this. This is mg which is written. Density into volume into g is mg. This is rho vg which is buoyant force, and 6 pi eta rv is your viscous force. So what they do, they are taking this to the left hand side. So rho s into rho s minus rho L. Rho s is the density of the solid. Rho L is the density of the liquid in which the body or the fluid in which the body is falling into g into v. Capital V is the volume of the body. Remember that. Okay. So we can write the volume assuming it to be spherical as 4 by 3 pi r cube. So things which can be cancelled, we'll cancel that out. Or you can say in our syllabus we'll only be dealing with the spherical cases. 1r also cancels this r square times. What else? 6 comes here, or we can say this is going to cancel 3 times. This is going to cancel 2 times. So 2, 3 into 3, 9. So 2 by 9 eta. There's only eta left here. Right, everyone? Only eta left here, and v which we are interested in finding. So 3 eta comes down, multiplies with 3, becomes 2 by 9 eta, rho s minus rho L, r square g. So if you ever forget, you can always derive it also. It's not that difficult. But if you can remember, that's fine. Okay. So rho s minus rho L, 2 r square g by 6 eta. That's the formula known as the terminal velocity. ठीक है, everyone? सर तो हम r वाले टर्म को मॉडिफाई करके भी दूसरे बॉडी का ड्राई फोर्स निकाल सकते हैं, एब्सोल्युटली निकाल सकते हैं, पर उस केस में हमें फिर उसकी वॉल्यूम लिखनी पड़ेगी अकॉर्डिंगली. दैट्स इट, भी निकाल सकते हैं, बिल्कुल निकाल सकते हैं, हम लोग आराम से कर सकते हैं, बट जरूरत नहीं पड़ेगी अभी, पर हाँ प्रैक्टिकली कर सकते हैं. ठीक है एवरीवन? So is it possible to derive formulas in exam? Does it sound impossible? It will be stupid if you know the formula and still if you're deriving it. But if you don't remember it, then definitely the only option left is to derive it. टाइम हो या ना हो, अगर क्वेश्चन ही नहीं आ रहा होगा फॉर्मूले की वजह से, तो फॉर्मूला तो डिराइव करोगे ना यार. Nothing happened, Monish. We just derived the formula of terminal velocity, nothing else. V is the volume. V is the volume of the body. Sir, what if the ball moves horizontal? And why would the ball move horizontal? And if the ball moves horizontal, then obviously it will not be the case of terminal velocity. Then you will have to write the force which is trying to drive it. You will require that driving force, right? And you will also require the formula 6 pi eta RV, because that is what the force is going to be, the viscous force, right? Hope it is making sense. Is there any terminal velocity definition here? I think I gave you the definition here. This is the maximum velocity attained by object when it is falling through a fluid. Okay. Okay, everyone, let's get into problem solving. So, everyone, switching off the chart. If a steel ball of mass 0.27 kg of radius 2 cm is moving in the liquid, which has viscosity given to us, calculate the terminal velocity. That's what the question is asking us to find out. So, see guys, I don't remember the formula though. The terminal velocity is going to be what? 2 rho s minus rho l r square g by 9 eta. This formula is the formula. Okay, everyone. So, you see that density of the solid is not given. Density of the liquid is given. The mass of the steel ball is given. Its radius is given. G value we already know. Eta is given. So, basically, we need to find out the density of the solid. How will I find that? Mass divided by the volume. Correct? Simply. So that will give me the value of rho s. Rho l is given. Everything else is given. We'll put the value and we'll simply find out. So definitely a lengthy calculative question it is. So volume 4 by 3 pi r cube, putting up everything, it will give you 3.35 into 10 to the power minus 5. Easy for me to say because it is directly written there. But don't worry, a question like this will never be asked in JEE examination, but can be asked in your boards or in your school exams. So 3.35 into 10 to the power minus 5 meter cube is the volume. Finding the density, mass divided by that. Mass is given already in kgs. So density comes out to be almost 8059 or 8060. We can write that. So 2 divided by 9 eta. Density of both of them are separate, almost a difference of 60 into the radius square into g value. Okay. So simplifying it should give you this value. Okay. Yeah, that's why I said school exam. Boards में नहीं आते यार ये topic. 9th standard की चीजें पूछी थी क्या 10th में नहीं पूछी ना. ठीक है. चलो guys, series of problem solving for all of you. Everyone is ready? Quizzes? How many questions? One. नहीं यार मैं secret reveal नहीं करूँगा. बहुत सारे. करते जाओ. Solve करते जाओ. ठीक है. जब मन भर जाए तो class छोड़ देना. When you feel like I'm done, just leave the class or stop answering in that case. ठीक है. Question of the day भी end में. Yes. There is question of the day also at the end. Okay. Chalo. Switching off the chat so that you focus on the question, everybody. A small metal sphere is dropped through honey, and another identical sphere is dropped into a less viscous oil. So identical bodies, both are same bodies, are the same identical two metal spheres. One dropped in honey, another dropped in say water. So what will you comment about the terminal velocity in the second liquid comparative to honey? Giving you 45 seconds, and the time starts in 3, 2, and 1. Okay. That's good. Nice. Very good, everyone. Let's say the common sense. Obviously, the common sense says that if the viscosity is decreased, then the terminal velocity will increase, and any which way the terminal velocity is inversely proportional to eta. So that way it should increase. Okay. So next one. The terminal velocity of a small-sized spherical body of radius r falling vertically in a viscous liquid is given by the proportionality. So how terminal velocity is dependent on the radius of that body? Giving you 45 seconds once again, and time starts in 3, 2, and 1. Last 5 seconds now, everybody. Okay, time's up. Let's see. Directly formula based. Should be right for everyone. Very good. Load. So I don't need to say anything here. V is directly proportional to r square. So answer is option B. Okay. Next one, everybody. A small metal sphere of radius r, density rho, falls from rest in a viscous liquid of density sigma. Okay, liquid density sigma. And coefficient of viscosity eta. Due to the friction, the heat is produced. You have to find out the rate of production of heat when the sphere has acquired the terminal velocity. So the rate of production of heat is going to be proportional to which power of r? Okay, so first of all, heat will be produced only by air resistance, or you can say the viscous force. Okay, so you have to calculate the power developed by the viscous force. Viscous force is calculated as 6 pi eta RV. Okay, and power in general for any force is written as force and velocity multiplication, or you can say the dot product. So this velocity is basically the terminal velocity in the question. So you have to find out P is proportional to R to the power n. P is power, the rate of heat production per unit time, which means power. Okay, so thermal power is how much? R to the power n. So which of these is the correct answer? Giving you all complete 2 minutes, and your time starts in 3, 2, and 1. 1 minute gone. 1 more minute left. Okay, and the time is up. Let's see. Correct answer is option D. Actually, it is not difficult after giving you so much of information, so many hints already been given. Should not be the problem. So see guys, the force is already 6 pi eta r v, and v we just now saw is proportional to r square, right? Terminal velocity is already proportional to r square. So can I say that if I put this here, the force is already proportional to r square, that means it is proportional to r cube, and power is force into terminal velocity. Okay, that means it is proportional to this r to the power 3 and this r to the power 2. So power is going to be proportional to r to the power 5. Does it make sense to all of you? Right? Easy tha. This way. Yes. Okay. Okay, understood, Anamika. So everyone ready for the question of the day? Everybody ready for the question of the day? Get ready. Get ready. Question of the day coming up now. Let's hope ज़्यादा hype ना create हो गई हो. Switching off the chat. A solid sphere of radius r acquires a terminal velocity v1 when falling through a viscous fluid having a coefficient of viscosity eta. So there is one solid body whose radius is r, it is falling, and it acquires a constant terminal velocity v1. Okay. Now, if this sphere is broken into 27 identical small spheres, 27 identical small spheres of same density, obviously, and each of these is now allowed to fall, or maybe one of them is allowed to fall. One of them is also possible to be allowed to fall in the same liquid. But this time, the smaller sphere, okay, is going to acquire a velocity v2, terminal velocity v2. What is the ratio of the velocity acquired by the bigger sphere to one of the smaller spheres? How much is the ratio of their terminal velocity? Giving you people 2 minutes to think about it. Only thing that I can tell you, the total volume of the bigger sphere and the total volume of the smaller spheres, total volume is going to remain the same. Density is same. And the time starts in 3, 2, and 1. Okay, 45 seconds remaining now. Only 30 seconds left. Come on, everyone. Velocity is directly proportional to square of the radius of the body. The terminal velocity is directly proportional to the square of the radius of the body because both are falling in the same liquid. So it's viscosity dependency here. Last 5 seconds now. And the moment of the truth, let's see. Actually, question was not worth 2 minutes, to be very honest. Question was not worth 2 minutes. Yeah, if you have the bigger ball of radius r, can I say its volume is 4 by 3 pi r cube? Right? Actually, you can eliminate option B and C because more be the radius, more be the velocity. Absolutely. So 27 balls, each having volume 4 by 3 pi small r cube. लिख सकते हैं, sir? Can I write this, everybody? So 4 by 3 pi gets cancelled. What will I say? R cube root of 27. So everyone knows this, right? Good enough. So V1 by V2 is going to be r by small r ka square. This is 3r by r square. That's 9:1. Make sense? That's it. That's it. The answer. Why more the radius, more the velocity? Okay. Okay, so everyone, these are the things that we have studied today. Viscosity definition, Poisson's equation, Stokes law, and terminal velocity. Okay. Sir, can you go to units of just a second, Harshan? We will. बात करेंगे अभी, रुक जाओ. बात करेंगे. The leaderboard for the day, everyone. ठीक है. So congratulations to everyone. Good job. And this is for all of you and Team India also. This is for Team India. Okay. And the next one is for Afghanistan. This is for Afghanistan today. Yes, everybody. Because Afghanistan is on a roll today. अभी क्लास के बाद में जाके देखो मैच में क्या चल रहा है. Sir, can you please show once again the question of the day? Absolutely, I can show you that, and it is here. Sir, धोनी को कल बहुत याद किया. किसने याद नहीं किया धोनी को? Afghanistan, sorry, Scotland has lost 5 wickets. Okay. Sadiq, wait. Sadiq, it's not wait for some time. Ashan, are you there? Hello, Ashan. Okay. Now I can hear you. And you want us to go to the slide where units are there? Yeah, this one. Tell me. Tell me. You're asking when it enters or before it enters, it starts burning. When it enters, when the viscous force starts to act on it, burns because of the viscous force. Okay. Okay, Samantha, bye bye. Who else was asking for a doubt? Tushit. Yes, Tushit. Can you hear me? Tell me. In our syllabus, we don't have. In our syllabus, we don't have. Otherwise, when you will enter into your engineering days, in graduation time, definitely those situations will be studied, especially if you are entering into certain type of engineering courses. Okay. But as of now, don't worry. No. Ray optics is already done, Shivansh, on YouTube. Sir, in terminal velocity wala part, after it reaches equilibrium, still the viscous force increases or not? As it's still moving. Okay. I have no answer to this question. Dilraj, I have no answer to this question because it's an operational question. So, sir, do not decide that. Yes, Vidya. Yes, Vidya. I got your question. I'm explaining it to you. So, you can see that this force is directly proportional to velocity. The only thing which can change basically when the body is moving. If this becomes constant, can I say this becomes constant? Do you have your answer now? So, if the velocity becomes constant, the viscous force becomes constant. And that is why equilibrium is achieved. Otherwise, there is no equilibrium. The net force acting on the body becomes zero. Okay. Cool. Okay, bye-bye. Yes, Aman. Good evening, bacha. Bolo. I'm good. I'm feeling I had like a lot of biscuits before the class. So, मुझे acidity हो गया. Yes, I understand. बताओ बताओ. सबके पूरे देश के दिमाग में वही चल रहा है. मोदी जी के दिमाग में भी वही चल रहा है. बोलो बोलो बोलो. स्लाइड 12 पे आ जाते हैं. स्लाइड नंबर 12 बोलो. वो एक्चुअली ये बताना चाह रहा है कि सबसे ऊपर ये एक्चुअली ट्रीटेड नहीं है, सिर्फ यहाँ पे भी लिक्विड है. तो ये बताना चाह रहा है ये वेलोसिटी प्रोफाइल है. ये बताना चाह रहा है कि ये वाली लेयर जो है ज्यादा फास्ट आगे आ गई है. ठीक. तो लिक्विड जब फ्लो करेगा ना तो टॉप मोस्ट लेयर सबसे फास्ट मूव करेगी. कि एक्चुअली सिर्फ वो नहीं बता रही कि वैक्यूम क्रिएट हो गया. वो सबसे कम मूव करेगा. वो ये बताना चाह रहा है. सबसे स्लो मूव करेगा या मूव ही नहीं करेगा. हाँ. हाँ. या वही मैंने बोला कि सेंटी वर्ड डज नॉट मेक सीजीएस यूनिट. वर्ड सेंटी होने से सीजीएस यूनिट नहीं होती ना. वरना तो फिर जैसे मास है. मास की सीजीएस यूनिट क्या है? ग्राम या सेंटीग्राम? ग्राम ही है ना. पर सेंटीग्राम भी पॉसिबल है क्योंकि सेंटी, किलो, मेगा, माइक्रो, नैनो ये प्रीफिक्सेस हैं. ये सिर्फ 10 टू द पावर्स को रिप्रेजेंट करते हैं. तो ये 10 टू द पावर -2 का मतलब सेंटी होता है. जैसे 10 टू द पावर -3 का मतलब क्या होता है? मिली होता है. एग्जैक्टली. तो वो भी यूनिट नहीं डिफाइन करते. वो सिर्फ 10 टू द पावर डिफाइन करते हैं. ये प्रीफिक्सेस कहलाते हैं. है ना. जैसे कि अलग-अलग वैल्यूज लिख लेते हैं यहाँ पे सबके काम आ जाएगी. ये तो एक्चुअली यूनिट्स एंड डायमेंशंस में किया जाता है. जब हम 10 टू द पावर 6 लिखते हैं तो इसको मेगा. जो काम किया मैं सिर्फ वही याद रखता हूँ और वही याद रखने बोलता भी हूँ. ये किलो हो गया. फिर आता है 10 टू द पावर -2 डायरेक्टली सेंटी. 10 टू द पावर -3 इज मिली. 10 to the power -6 is micro, and 10 to the power -9 is nano, और 10 to the power -12 is pico. Pico काम आएगा लास्ट चैप्टर ऑफ फिजिक्स में. हाँ, 10 to the power -10 भी काम आता है एक्चुअली. एंगस्ट्रॉम, नॉट एंगस्ट्रॉम, एंगस्ट्रॉम. एक मिनट बाद चलते हैं. इसका नेक्स्ट सवाल था ये. हाँ, ये वाला. 1 लीटर जो होता है ना वो 10 to the power -3 मीटर क्यूब होता है. ये कन्वर्जन याद रखना. ऐसा बोल सकते हो 1 मीटर क्यूब जो है वो 1000 लीटर होता है. ऐसे याद रख सकते हो. इसको विजुअलाइज में कैसे कर सकते हो. 1 मीटर लगभग ये साइज होती है. तो इतना बड़ा मतलब अपने अपने हाथ के बराबर 1 मीटर होता है. यूजुअली अपना जो हाथ होता है 1 मीटर है. तो ऐसा इतना लेंथ, इतना ब्रेथ और इतना हाइट का एक क्यूब बनाओ. है ना. तो उसमें कितने बिस्लेरी के 1 लीटर बॉटल खाली हो सकते हैं. दैट इज व्हाट इट इज. तो 1000 लीटर बॉटल्स आ जाएगी उसके अंदर. इतना बड़ा क्यूब होता है. ठीक है. या राइट. सर, डज विस्कोसिटी अफेक्ट डेंसिटी? बड़ी केमिस्ट्री लेवल का क्वेश्चन है. डज विस्कोसिटी अफेक्ट डेंसिटी? rather उल्टा ही पूछना चाहिए. डज डेंसिटी अफेक्ट विस्कोसिटी? मुझे लगता है डेंसिटी और विस्कोसिटी में डायरेक्ट कोरिलेशन है. अगर ज्यादा डेंसिटी होगी तो चांसेस है कि ज्यादा विस्कोसिटी भी हो. पॉसिबल है. बट इट एक्चुअली विल बॉयल डाउन टू कोएफिशिएंट ऑफ विस्कोसिटी मोर. राइट. एक जनरल कोरिलेशन तो बोल सकते हैं, बट ऐसा कुछ फॉर्मूला तो नहीं है कोई भी, ठीक है। सर अगर प्रैक्टिकली करें तो 20,000 का खर्चा होगा, आई नो शिका, इसलिए वो करना मत। 20 लीटर की बाल्टी होती है घर में, उससे कर सकते हैं। घर में जो 20 लीटर की बकेट है ना, वाटर बकेट, उससे भी कर सकते हैं। नंबर ऑफ बकेट्स भी कम भरने पड़ेंगे, तो घर में मम्मी पापा को लगेगा कि आज थोड़ा घर का काम भी कर रही है शिका। सर क्या वो आपकी स्पेस जाने का है? मैं कब स्पेस जाने वाला था, मैंने तो पहले मना कर दिया कि मुझे स्पेस नहीं जाना, आई एम ऑलरेडी इन स्पेस। सर रेन ड्रॉप्स में कभी एमजीबी ओवरकम हो सकता है क्या? एमजीबी ओवरकम हो सकता है मतलब व्हाट इज दैट सपोज्ड टू मीन? आई नो शिका, मैं इलॉन मस्क के साथ जाने वाला था, इलॉन मस्क मेरे साथ जाने वाला था शायद। यस शिवांश, गुड इवनिंग। आई डिडंट गेट योर क्वेश्चन यार, द क्वेश्चन इज कम अगेन, व्हाट अगर हो ही नहीं सकती। तो बाइंड फोर्स तो कभी भी अगर बात करें तो बाइंड फोर्स जो है वो डेंसिटी ऑफ द लिक्विड पे डिपेंडेंट है, और एमजी जो है उसमें डेंसिटी ऑफ द सॉलिड इन्वॉल्वड है। 90% ऑफ द केसेस में सॉलिड की डेंसिटी ऐसे केसेस में लिक्विड से ज्यादा ही होने वाली है, स्पेशली जिन केसेस को हम बात कर रहे हैं। तो बाइंसी तो डेफिनेटली वेट को ओवरकम नहीं कर रही, वरना रेन ड्रॉप्स हवा में फ्लोट कर रही होती, नीचे नहीं आती। हाँ, लेकिन वही बात है, अब ड्रैग फोर्स भी जो है वो वेलोसिटी पे डिपेंडेंट है। तो ऐसा होने के लिए कि जो एयर रेजिस्टेंस है वो एमजी को बैलेंस कर जाए, और इतना बैलेंस कर जाए कि बॉडी ऊपर जाने लग जाए, वो होने के लिए यू विल एक्चुअली रिक्वायर अ वेरी स्ट्रांग विंड फ्लो, देन दैट मे हैपन। और स्ट्रांग विंड फ्लो चाहिए तब ऐसा हो सकता है, जो कि हमने बात की थी लास्ट टाइम बर्नौलीज एप्लीकेशन में, हाउ एरोप्लेन्स फ्लाई, या फिर जो छत होती है वो कैसे उड़ जाती है, वो उसका प्रैक्टिकल एप्लीकेशन तब बनता है। तब वेट से भी ज्यादा फोर्स अपवर्ड लगता है बिकॉज़ ऑफ प्रेशर डिफरेंस एक्चुअली। क्योंकि होगा क्या, अगर तुम ये सोचो कि कोई भी बॉडी ऊपर जा रही है, नीचे ना आके ऊपर जाने लग जाए, मान लो यही बॉल या ये वाटर ड्रॉप जो नीचे गिर रही है ऊपर जाने लग गई, तो वेलोसिटी का डायरेक्शन ऊपर हो गया, तो उससे विस्कस फोर्स का डायरेक्शन एमजी के डायरेक्शन में आ जाएगा। तो विस्कस फोर्स को इस बात से मतलब नहीं है कि कितनी वेलोसिटी, इस बात से मतलब है कि किस डायरेक्शन में बॉडी मूव कर रही है, उसके अपोजिट एक्ट करना है। तो अकेला बायंसी को तो ऊपर लेके जा नहीं सकता, तो एमजी के साथ फिर फ्रिक्शनल फोर्स भी ऐड होने लग जाएगा, तो देयर इज वेरी लेस चांस नेचुरली दिस टू हैपन, है ना। यू विल रिक्वायर लाइक रॉकेट टाइप का सिचुएशन कि भाई एक इंजन भी लगा हुआ है जस्ट ट्राइंग टू टेक द बॉडी अप। या ओके, सारे के फान यू आर हियर, यस आशीष, गुड इवनिंग बच्चा, बोलो बोलो ना। मोमेंट ऑफ इनर्शिया की बात कर रहे हो, उसमें क्या डाउट है, मतलब क्या नहीं समझ में आता उसमें? अरे यार देखो, मान लो अगर ये एक डिस्क है या ये एक स्फीयर है, और आई डोंट नो उसका रेडियस क्या दिया हुआ है, जो भी दिया है, तुम्हें ये मालूम है कि जो पहले स्फीयर था, स्फीयर ले लेते हैं इसको, उसका मोमेंट ऑफ इनर्शिया 2/5 m स्क्वायर था। अब मान लो तुमने एक ऐसा स्फीयर क्रिएट कर लिया है जिसका खुद का रेडियस जो है वो r/2 है, सॉरी कैविटी क्रिएट कर दिया जिसका रेडियस r/2 है, तो कैविटी से कितना मास निकाला वो निकाल सकते हैं, सेम डेंसिटी है ना। तो डेंसिटी का मतलब है मास अपॉन वॉल्यूम, तो ये हो गया तुम्हारा वॉल्यूम ऑफ द कैविटी वाला मास। तो मैंने मान लिया m डैश मास निकाला मैंने यहाँ से, ठीक है, बात समझ में आई। तो और पहले जो मास था वो कैपिटल M था, और पूरे स्फीयर का वॉल्यूम था 4/3 पाई r क्यूब। तो यहाँ से तुमने देखा कि m डैश का वैल्यू है कैपिटल M स्मॉल r क्यूब बाई कैपिटल R क्यूब, ये भी आ गया, ठीक है। अब मुझे क्या करना है, जो मोमेंट ऑफ इनर्शिया होता है बचे हुए पार्ट का आई डैश, उसमें मुझे करना क्या होगा, एक्चुअल मोमेंट ऑफ इनर्शिया की वैल्यू निकालूंगा, और उसमें से इतने पोर्शन का मोमेंट ऑफ इनर्शिया सबट्रैक्ट करूंगा। क्यों करूंगा, क्योंकि उतना मास निकाल दिया मैंने, ये जो कैविटी बना दी ना, इस कैविटी का मोमेंट ऑफ इनर्शिया निकालना पड़ेगा। और कैविटी का मोमेंट ऑफ इनर्शिया कैसे निकालूं, पैरेलल एक्सिस थ्योरम से। तो पहले लिखना पड़ेगा 2/5 m r स्क्वायर, स्मॉल r लेना पड़ेगा, विच इज बेसिकली r/2। उसमें कितना डिस्टेंस से शिफ्ट किया, पहले एक्सिस ऑफ रोटेशन यहाँ होनी चाहिए थी, अब यही इसका dv है, तो m into d which is also equal to r square, ऐसे हो जाएगा, ऐसा ही बस। तो यहाँ से वैल्यू निकालना, इधर प्लेस करना, कैपिटल I का वैल्यू आंसर आ जाएगा, नंबर ये करना है। ओके नेक्स्ट, सादिक इरफान, आर यू देयर? हाँ सादिक, चल एकदम बढ़िया। देखो पहली बात तो जेई की प्रिपरेशन कभी कंप्लीट नहीं होती, यू कैन नेवर से मेरी जेई की प्रिपरेशन कंप्लीट हो गई है, कभी नहीं बोल सकते, ठीक है। तो सबसे बड़ी इंपॉर्टेंट चीज़ ये है, व्हेन जब भी हम पहली बार जेई के लिए कोई चैप्टर पढ़ते हैं, तो उसमें हम कभी भी सारी एक्सरसाइजेस कंप्लीट नहीं कर पाते। इनफैक्ट जो स्टूडेंट्स डमी स्कूल से जुड़े हुए होते हैं वो भी नहीं कर पाते, बहुत डिफिकल्ट होता है वो, क्योंकि क्लास डायनामिक है, कम से कम 3 सब्जेक्ट पे तो ध्यान देना ही है, फिजिक्स केमिस्ट्री मैथ्स पे, तो कितना भी हाँ दे पाते हैं, उसके बाद ये भी नहीं सकते प्रैक्टिकली, कोई भी नहीं दे पाता, चाहे फिर वो मैं वही बोल रहा हूँ डमी स्कूल वाला बच्चा भी नहीं दे पाता। तो सबसे ज़्यादा जरूरी क्या है कि मैं ज़्यादा से ज़्यादा वैरायटी ऑफ क्वेश्चंस कर पाऊँ, वो जानना मेरे लिए बहुत ज़्यादा जरूरी है। अब एक्सरसाइज सॉल्व करते समय मेरा टारगेट ये नहीं होना चाहिए कि यार सारे क्वेश्चन हुए या नहीं हुए, ये होना चाहिए कि अगर मैंने क्वेश्चन कर लिया और अगला क्वेश्चन मुझे दिखाई दिया बिल्कुल वैसा ही सवाल है, तो मैं नहीं करूँगा उसे, क्योंकि उसे करना सिर्फ और सिर्फ मैं टाइम कंजम्पशन, उसमें मैंने कुछ सीखा नहीं ना नया। तो मेरा टारगेट होना चाहिए कि मैं एक्सरसाइज कंप्लीट कर रहा हूँ ना, जब तो मैं ज़्यादातर वैरायटी ऑफ क्वेश्चंस देख पा रहा हूँ, और पहले एक्सरसाइज 1 फिर एक्सरसाइज 2, ये दो तो कम से कम मैं कर पाऊँ मिनिमम। अगर मैं पहले अच्छे से मैं बोल सकता हूँ कि अगर तुम जैसे मैंने पहले भी बोला, मैं बहुत बार बोल चुका हूँ कि डिपेंडिंग अपॉन द टाइम अवेलेबल, अगर मान लो एक एक्सरसाइज में 100 सवाल है, 100 क्वेश्चन है, और मेरे पास अवेलेबल ही 2 दिन है, तो शायद मैं नहीं कर पाऊंगा 100 क्वेश्चंस। तो मेरा तरीका होगा सॉल्व करने का ऐसा कि मैं ये डिसाइड करूंगा मैं कितने घंटे पढ़ने वाला हूँ, इस एक्सरसाइज की सॉल्विंग कितने घंटे कर सकता हूँ, उसके हिसाब से आई नो कि मुझे जनरली कितना टाइम, 1 घंटे में कितने क्वेश्चन कर सकता हूँ। अगर मैं पूरी एक्सरसाइज को से मैं 5 घंटे दे पाऊंगा, ठीक है, और मैं हर घंटे में 10 सवाल ही कर सकता हूँ, दैट मींस 5 घंटे में 50 क्वेश्चन ज़्यादा नहीं कर पाऊंगा, टू बी रियलिस्टिक। तो मुझे आउट ऑफ 150 क्वेश्चन करने हैं, तो मेरा सही तरीका होगा कि मैं ऑल्टरनेट क्वेश्चन करता चला जाऊंगा। बीच में अगर मुझे कोई क्वेश्चन ऐसा दिख गया जो करना ही चाहिए, उसको डेफिनेटली करूंगा, हार्ड एंड फास्ट नहीं होगा कि पहला करूंगा फिर थर्ड करूंगा फिर फिफ्थ करूंगा फिर सेवंथ करूंगा। मुझे लगा 6 क्वेश्चन ज़्यादा अच्छा दिख रहा है वो करना चाहिए, 7th उसका रिपीटेशन है नहीं करना चाहिए, तो मैं छोड़ दूंगा। ऑल इन ऑल मैं कोशिश करूंगा कि मैं लास्ट क्वेश्चन तक टच कर पाऊँ 5 घंटे में। ये होना चाहिए टारगेट, एंड यू कैन कॉल इट अ कंप्लीशन ऑफ वर्क, क्योंकि जब तुम दोबारा से कभी रिवाइज करोगे चैप्टर का, जब कोई क्यूमुलेटिव टेस्ट आएगा, तब तक तुमने ऑलरेडी उन क्वेश्चन को मार्क भी कर लिया होगा जो तुमने कर लिया ऑटोमेटिक डिवीजन में। तो जब दोबारा रिवाइज करोगे तो सिर्फ इन हाइलाइटेड क्वेश्चन को करोगे, और जो क्वेश्चन तुम अटेंड नहीं कर पाए थे उन्हें अटेंड करोगे। दैट इज वेयर दिस इज कंप्लीटेड। इट्स मिक्स ऑफ बोथ, इट्स मिक्स ऑफ बोथ, इट्स मिक्स ऑफ बोथ। दोनों को ही सही टाइम पे सही इंपॉर्टेंस देना जरूरी है। मतलब मैं जब क्वेश्चन सॉल्व करता हूं एक्सरसाइज में, तो मैं प्रेशर से ना करूं कि मेरा टेस्ट है, ठीक है, और जब मैं एग्जाम दे रहा हूं, टेस्ट दे रहा हूं, तो मेरे दिमाग में ये प्रेशर नहीं होना चाहिए कि मैंने तो एक्सरसाइज से 50 सवाल ही किए हैं। दोनों इंटररिलेटेड है, पर तुम्हें इंटररिलेटेड नहीं रखते हुए प्रिपेयर करना है। मतलब तुम्हें दिमाग में प्रेशर नहीं लेना उस चीज का। यू हैव टू टेक टेस्ट आल्सो एज पार्ट ऑफ लर्निंग। टेस्ट भी तुम्हारा लर्निंग प्रोसेस का पार्ट है, ये याद रखना हमेशा, क्योंकि बहुत सी चीजें हम उस एग्जाम के प्रेशर में नहीं सीख पाते हैं। बहुत बार हमारा दिमाग जो घर में नॉर्मली क्वेश्चन सॉल्व करते समय नहीं सोचता, वो एग्जाम में सोच पाता है उस प्रेशर में। तो हमें उस स्टेज तक पहुंचना है जहां पे एग्जाम में हम नर्वस नहीं होते, क्योंकि जब तुम वो नर्वसनेस के लेवल से थोड़ा आगे निकल जाओगे ना, तब तुम्हें समझ में आएगा कि बहुत से क्वेश्चन जो है जो यूजुअली करते समय हम थोड़ा सा बैकवर्ड पे चले जाते हैं, ये नहीं होता लग रहा है। एग्जाम में क्योंकि प्रेशर होता है ना, तो दिमाग प्रेशर में और ज्यादा फास्ट सोचता है। तो बहुत बार मेरे साथ हुआ है, बहुत सारे स्टूडेंट्स के साथ ऐसा होता है कि एग्जाम में क्वेश्चन बन गया जो घर पे नहीं बन रहा, ठीक है। So you're doing right, you're doing fine, absolutely fine. Don't try to be very don't try to be very hard on yourself. You're doing good. Just try to not take negatives out of this more. Try to just improve as much as we can, है ना। ठीक है सर, 11th में तो डमी स्कूल नहीं लिया एंड अब रिग्रेट हो रहा है, बिकॉज फिर सेल्फ स्टडी के लिए बस 2 घंटे ही मिल पाते। तो सर 12th में डमी लेना ठीक होगा? मिलता है तो ले लो यार। एक्सक्यूज मी सर, नर्वसनेस तो होता ही है एग्जाम में। हाँ बिल्कुल होता है, होना ही चाहिए। टेक रोहित शर्मा यस्टरडे फॉर एन एग्जांपल। नर्वसनेस का फायदा भी है बिल्कुल। नर्वस नहीं होगे तो और कॉन्फिडेंट हो जाओगे। सर कल मेरा बर्थडे भी था। ए दिव्यांशु यार, मतलब शुड आई से हैप्पी बर्थडे वंस अगेन और शुड आई सिंपैथाइज विद यू? तेरे लोगों ने तुम्हारा बर्थडे सेलिब्रेट नहीं किया होगा ज़्यादा। आई नो। कल इंडिया के टीवी फोड़े थे। हाँ निहाल, बोलो बोलो बोलो। अरे यार इंडियन टीवी नहीं तोड़ते सर। 31 के रेस में रोटेशन आ रहा है। अरे तुम सब तैयार हो यार एकदम, रोटेशन को फोड़ के आओ। रुको निहाल, मैं म्यूट करता हूँ। यस निहाल। हाँ एक्स टू द पावर 3 राइट। Right? Between what point to what point? Question is asking to calculate the work done, right? They're asking about the change in kinetic energy, and that is also expression then. I'm talking about the options. So that means they're telling you from which x value to which x value. X equal to 0 to x equal to 2. You want to find out. Mass of the body given. So you just put the value of x here, you put the value of x here, get the value of v1 and v2, and half mv2 square minus v1 square. That's the answer. See, v square comes out to be, if you square both of these, this is 25x cube, right? Correct? You made this mistake? Limit. Then just do this. Half mv square is going to be half whatever be the mass value, multiply that here, and change in kinetic energy, you know, half m v2 square minus v1 square. That's it. That's going to be the answer. Maths I can't say, but physics it's definitely visualizable. You can visualize that. How can you not? Think about it. Think about it. Think about it. That's okay. Thinking about formula is fine, but once you're done thinking about the formula, after that, think about the situation also. That what's happening in the question. Once you're done with the question, after that, think about the question. That what does it mean? The value that I found. It will open up a lot of. It will open up a lot of methods for you to sometimes make question easy for you to solve. Okay. See again, common sense is only used when we usually use it. When you're not just trying to use it in our exam, we usually use it. Then only it works. In our day-to-day life, when we think about things from our common sense first, before we think about things from physics or science, then only the common sense is our friend, right? Otherwise, they say that common sense is not so common. So it happens only if you keep on thinking about formulas in the examination. Then that lateral thinking will not develop. You need to develop that lateral thinking, that you are thinking about the question, what is happening in it. Then also parallelly might be thinking about the formula to apply. Okay, so in the beginning you can try to do this, that you're solving a question by the formula, you're able to solve it. Then think about the question, what has happened in the question. That's okay. That's okay. Whatever time you're spending, what is important is to develop a skill. You're developing a skill of problem solving, and problem solving is not formula application. Remember that. Okay. What? This one. This was a challenging one. That's why I gave the approach to the question. This was a challenging one. I understand that. It happens. At times it happens. And especially, this is not the right example to discuss because you guys have not studied this in mathematics yet, the calculus part. That is why. So it will not look. Okay. I understand that. But arriving here is something which comes only by practice. And when you're saying practice, this question does not say it on the face that what formula to apply and how to apply. Exactly. And unless you will develop that lateral thinking that I'm again stressing upon. If you'll always think about the formula while reading the question, this type of question will always create a problem. Or I should say 60 to 70% of JEE problems will create a problem. Remember, our objective is not to do exercise. Our objective is not to complete assignments. Our objective is to learn how to solve problems. Some people learn that by solving only 50 questions per chapter. Some people take 100, 150. Some people take 500 questions to develop that thinking. But what matters, are you consciously trying it or not? Getting? You solve 10 questions only. But if those 10 questions, you consciously try to solve them by understanding what is happening in the question and arriving by yourself that I think this formula should work in it. That is what matters. Formula is just the last part, or you can say formula is only to not do the derivation all the time in a question. That is why we apply the formula. Okay? Understood, Kamal? Not able to sleep at night? Try meditation. Session is ending in 5 minutes. Start again. Try meditation. It helps. There are meditations to help you sleep. You'll find them on maybe YouTube. You'll find them on maybe any of the audio websites like Amazon Music or Savan. I don't know whichever you use. If you don't, that's fine. You can go with YouTube wala thing also. Meditation to sleep. Simple. Okay. Listen to that. Try to sleep today with that. It'll help you. Definitely help you. Okay. Take care. Bye. Sir, I feel I need to revise everything from starting, and with offline schools, I have no time to start it up again. Please help. Watch YouTube videos, Kunjan. Watch YouTube videos of one-shots. One-shot videos are helpful in revising in 1 hour. Okay, Kunjan? You just search for the topic one-shot, whichever you find. I'm not even saying JEE videos, as in Vedantu JEE. You find it anywhere. You find that one is working for you, just go with it. Okay? Cool? Yes. There is a one-shot series going on, but we are not doing every chapter in that. So if you want to follow that, you can follow that also. Okay. Chalo everyone, the session is about to end. Anyway, I don't want the session to end randomly. Let's wrap it up. We'll meet again on Wednesday. We'll continue. We'll be having last session of fluid mechanics in that. Okay? Yes, everybody. So good night. Hasta la vista, sayonara. Yes. Bye-bye. See you all next time. Bye-bye.